Alright, you guys, so for number 6, the math is not that hard, but the concepts are really hard to grasp. So let's go piece by piece. On the one hand, they tell us, for some reason, that the side lengths x centimeters of an buzzword equilateral triangle are increasing at a rate of 4 centimeters per second. They also tell us, or the question really, is to find the rate, so find the rate at which the area of the triangle is increasing when the side lengths are 5 square root 3. And so this exercise, as I said, is pretty hard in terms of concepts, but in terms of math, it's very straightforward. Like I could show you the math lines in less than a minute and just show you the answer, but I really need you to understand why we're doing what we're doing. And so let's go piece by piece. On the one hand, we've got the famous equilateral triangle. Now you guys, you usually run into 3 types of triangles, okay? On the one hand, you have the isosceles. On the other hand, you have the equilateral. And last but not least, you might be facing this thing called the scalene triangle. And so the isosceles is a little bit more of a classic, It has 2 sides which are the same, and therefore 2 angles which are the same. And it has one last sort of angle or side which is different. See? For the equilateral, following its name, equilateral equal, all the sides are the same. And all the angles, therefore, are also the same. Now, here's a quick comment that I'm going to make, which is key information. And so, with an equilateral, okay, or with a triangle, better said, the degrees, how much do they add up to? A triangle will always add up to 180 degrees. And so in an equilateral triangle, because you have 3 different angles, right, 1, 2, 3, you can take that 180, divide by 3, and find out that in an equilateral triangle, all the angles are 60 degrees. So all angles are 60 degrees. And last but not least, the scalene is just this weird kind of thing which has 3 different sides and therefore has 3 different angles. Okay, so the scalene is just all over the place. Okay, for today, for this exercise, we're focusing on the equilateral triangle, and the key information here is that all angles equal 60 degrees because all angles are the same. So you do 180 divided by 3, you get that 60. Okay. On the other hand, we need to find, that being said, right, we now need to focus on finding the rate at which the area of the triangle is increasing. See? Now there's a lot of moving parts here, quite literally. On the one hand, this imaginary triangle that we have has side lengths x centimeters. So let's go ahead and draw that now. So this equilateral triangle of the exercise has a bunch of sides with x. See? And you also know that all of these are 60. All right, so there is my equilateral triangle. Now this equilateral triangle is increasing its sides at a rate of 4 centimeters per second, right? And so having this in mind, you need to find the rate at which the area of the triangle is increasing. Which makes sense because if 1 second your triangle is this big and the next second it's this big, then the area increased. And so the question of this exercise is, okay, at which rate is the area increasing, especially when the side lengths are 5 square root 3. Okay, that's the question it's trying to ask. First of all, the area is going to get bigger, of course, and at which rate is it getting bigger? Exactly at 5 square root 3 for the side lengths. See? So, that is a little bit the context of the problem. Let's go ahead and try to make an area formula. And so if you go ahead and try to make an area formula with the OG one, right? Well, there's 2 different area formulas that we can use. So you can use the classic, which is base times height divided by 2. And being an equilateral triangle, you can probably figure that out in terms of x. Or you can also go ahead and use the sine sort of or trigonometry version of the area of a triangle, which is in your formula booklet and goes like this: 1/2 times a times b times sine c. Now, all this is really saying, or asking for, better said, is that for an area of a triangle, all you need, okay, is some angle C and the sides A and B that are next to it, okay? So you can get the area of a triangle if you have these dimensions. This guy here, and this angle there. See? You can also get the area of a triangle if you have this side here, and that angle there. And you can also get the area of a triangle if you have this side here, and that angle there. So all I'm really saying is like, okay, for the sine area trigonometry thingamajiggy function formula, okay, for this guy here, all you need is one angle and the sides next to it. And do I have an angle and the sides next to it? Heck yeah, I do. I know that all the angles are 60 degrees. And so following the formula on the right, you can't do it with the one on the left, but I'm going to do it with the one on the right. Following this formula, you can end up with 1/2 times, for example, we'll be using these, see? So A times B, times B, right? Times sine C, the one in the middle, so sine 60, right? And so this is my current area formula for this equilateral triangle. You have 1/2 x squared times sine 60. Now, no one likes how sine 60 looks like because we don't have a calculator. For paper 1, we don't. And so you want to find a way, right? You want to find a way to put that sine 60 in other terms, right? So you can be thinking radians, this or that, etc. Eventually, you should be remembering from your unit circle, see? Eventually, you will remember from your unit circle, and this is the kind of thing you have to learn. From your unit circle, you have the 60 degrees right there, okay? And here you have a point which goes, I think it was 1/2 comma square root 3 divided by 2. And so sine, let's remember that sine is slope, right? And so that means that sine is opposite over hypotenuse. Now in the unit circle, all your hypotenuse are equal to 1 because the radius equals 1 in all of these, see? And so all you're left with for sine 60 is just focusing on the opposite. The opposite, take a moment and notice that the opposite is, right? The opposite is your y value, okay? So the y value when sine is 60 is square root 3 divided by 2. So all that really was a quick explanation that the area is actually 1/2 x squared, x squared times square root 3 divided by 2, all right? And now is when the exercise gets really juicy. Okay, so now is when we do the big sort of leap and to try and find the rate at which the area of the triangle is increasing, see? And so first, let me do a quick explanation of what derivatives are, how they work, like a general sort of intuition, see? So if you have a normal, just like a normal function, see, imagine you have a function that goes like a parabola, that goes like this, see? If you haven't done anything to this parabola, okay, if you haven't done anything to this parabola, then that means that plugging in x will get you a value for y, see? So for example, I don't know, if you plug in x of 1, you get a y of 2, you plug in x of 3, you get a y of 9. All this is giving you is a bunch of different points. This gives you the point 1, 2. This gives you the point 3, 9, right? So here's 1, 2, here's 3, 9. I'm just making up the information, but the point is, if you have not done any derivative yet, plugging in an x gets you a value for y, see? But the moment that you have the derivative, see? So this is the original, see? Original, unchanged, blah, blah. The moment you have the derivative, it's a little bit different. Because now, if you plug in an x, you don't get a y, you get a slope. Or better said, your y value turns into a slope. So for example, if you plug in an x of 1, maybe my slope would be like, I don't know, 1 as well, see? So that means that an x of 1, okay, my slope is approximately 1, see? For example, an x of, I don't know, 2, see, might give me a slope of 0.5. Because at an x of 2, it's a little bit more flat, right? And so you end up with a slope that is closer to 0, see? So point is, all I'm really trying to tell you is that every time you do the derivative, you are now looking at slope, see? And slope, we also associate it to rate of change. And so anytime you do the derivative of something, you're really finding the rate of change of whatever that is. Okay, so the derivative helps identify the rate of change of whatever you're looking for, see? And so over here, it's super convenient because, oh, look at that. You need to find the rate. Well, isn't that just nice? right? And so from here, your formula for area, you can, clean it up a little. So for example, combine this 1/2 with this term over here. Your formula for area ends up being as x squared times square root 3 divided by 4, because of 1/2 times the 2 on the bottom, see? And so from here, if you want to find the rate at which the area of the triangle is increasing, all you really have to do is just find the derivative, see? And that helps you find the rate of changes I mentioned earlier, and you're pretty much good to go. However, there is one small tiny detail that we have to go over, and it's not exactly exciting, but it is worth knowing, see? Basically IB math. Just kidding. Point is, here, you're handling a special type of unit. Here you have an increasing rate, 4 centimeters per second. And so technically your area of the triangle is depending on two things. So the rate, this is the thing, so area of triangle is depending on two things. On the one hand, it depends on the fact that side increases by 4 centimeters per second. So that is the one thing that the area of the triangle depends on, that the side increases by 4 centimeters per second. But it also depends, obviously, by the current side length. And so from here, if you go ahead and do the derivative and plug in for x, all you're really doing is applying the current side length, see? And so let me first show the common mistake, which is actually how I was facing it earlier until I realized how to actually do it. If you do the derivative, you end up with 2x square root 3 divided by 4, and then you go ahead and plug in x with the side length, right? Because x is side length, and so you plug in x as 5 square root 3, and you find that the area has to be 2 times 5 square root 3 times square root 3 divided by 4, right? And this seems like the right play. It's probably what a lot of people do, including myself initially, until I took a closer look at it and realized, careful, the area of the triangle depends on two things. It depends on the side length increasing 4 centimeters per second and the current side length. And so the approach I just did in orange is only applying point number 2. It's only taking into consideration the current side length. And so the weird unit I was talking about is time. You have to consider time. This first one up here is time, right? It's increasing by 4 centimeters each second. You have to consider that, difference in time, see? And so technically from over here, you get a little bit fancy. You're not just doing the derivative with respect to x, you are doing the derivative of your area in respect to time. And kapow, this is the big step and big concept you need to grasp. So the rate at which the area of the triangle changes not only depends by the current side length, but it also depends of the side increasing by 4 centimeters each second. And so technically from here, what you need to do, like this is just very sort of like fancy math writing, but I think intuitively you're going to get it. And so on the one hand, you need to do the derivative, right, of this whole thing in respects to time, right? And so if you go ahead and do the derivative of this in respects to time, all you really end up with, I know that when it says in respects to time, it's kind of whack, but all you really end up with is the same derivative that I showed earlier, see? And so really what you end up with is the 2x square root 3 divided by 4, see? That's what you end up with. But because you're doing the derivative in respects to time, you have to acknowledge, x, my side length, is increasing by 4 each second. And so you also have to multiply this. And yes, you can big brain and just do like times 4 and bada bing bada boom, but really, like the fancy math language is saying that, x also depends, right? X also depends on time, see? And so here it's a little bit of a chain rule sort of thing going on, which on the one hand is, okay, so you need to find how the area changes in respect to time. So you do the derivative of x, or your area, right? Derivative of your area sort of like normally, quote unquote. But then you have to acknowledge, x itself depends on time, because x is the side length, and the side length is increasing by 4 each second. So you also need to put this term right there, see? So that is the big brain play you sort of have to do. Now, how much is x increasing per second per time, right? How much is it increasing? It's increasing 4. So technically you can plug in 4 right there. And also, what is x? Well, x is a side length, right? And they tell us to find the rate at which the area of the triangle is changing when the side length is 5 square root 3. So this is what you plug in for 5 square root 3 right here. See? So you go ahead and do all of that. You end up with 2 times 5 square root 3 times square root 3 divided by 4 times 4. See? So this looks long, this looks nasty, but go piece by piece. The hard part is over. All you really need to acknowledge was this thing right here. The area of the triangle depends on 2 things: the side length increasing by 4 each second, and your current side length. So once you do that, and you do the chain rule appropriately, you just gotta solve this basically. See, so this goes away with this, and you can end up with 2 times 5 times 3, because the square root 3 combines with the other square root 3, so basically you end up with this. This times this is going to be the same as this, is going to be the same as this, okay? So 2 times 5 times 3 is going to give you, well, this is 10, so 10 times 3, 30. So really, the rate at which the area of the triangle is increasing with the side lengths are blah, 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 are that amount, are 30 centimeters per second, okay? So that is for number 6. The math is not too hard, but the intuition is wild. Okay, the intuition, I'll be honest, is wild. It's hard to grasp. And the main thing I would focus you to realize, okay, or to study more deeply, is that this is a derivative in respects to time, all right? And so notice, whenever you have the derivative in respects to time, you gotta put this extra sort of term at the end, see? On the one hand, the area of the triangle, this is the thing. Let me do it like very colored, see? So on the one hand, for finding how the current side length affects, I'm putting it in pink, which is this whole thing here, see? And for the side length increasing by 5, which I'm putting in, I don't know, blue, see? It's this guy here, right? And so once you realize that and write it down accordingly, it all just sort of flows a lot more than what you think, see? So be careful, keep that in mind. Derivatives respects to time will always be done this way, see? The other way you can try to understand it is that right here, there was a chain rule, see? Because yes, you did the derivative in respects to time, but not yet like in respects to x. So this is in respects to time, then you gotta do it in respects to x, because x depends on time as well, because of this first line over here, see? So guys, I know it's kind of confusing. I explained it in as many ways as I could. That is for number 6, and I hope it helped.